Okay, now we're going into a new section of the Chapter 4. We've come back to this summary of the scenarios that we wanted to cover, and we've gone over the Emery modulation formats and the coherent detection, and now we're going into a section on non-coherent detection. So the non-coherent detection, we're not going to go over all the modulation formats, but just two for which this is a popular solution, and that is phase shift keying and frequency shift keying. Now, when we look into the performance of these systems, we're going to see a change because the error probability now has got to be calculated with non-Gaussian noise. And so this is a departure from the rest of the class where everything else is Gaussian. But when we go to non-coherent detection, it essentially becomes an energy detector. And because of this, the noise is being manipulated. It's no longer linear. And because of this, the noise statistics change. So we'll go over them to give you a feeling for, why we want non-coherent detection and what is the penalty in performance you might not come with a non-coherent approach. So again, this gives you a reminder of where you can find this information in the textbook. And in a case of non-coherent detection, basically the form of the receiver is a correlator like we have seen previously. But after the correlation, we're going to be squaring the results of the correlation. So we're squaring the statistics, and this is in order to come up with the, and then followed by a summation. So basically we're getting the energy of the signal. So, if you think of the two branches here, this is for the case of in phase and quadrature, it would be, in this case we're combining the two to get the signal energy. In the case of FSK, it would be very similar, except there would be one branch for each one of the signals. And of course, when you square it, again, you're getting the energy of the signal. You don't need to sum. The summation is part for the PSK case. But the squaring is in order to get, like something that's basing the decision based on the energy. So this is a nonlinear receiver. So remember, the previous cases, we looked at simply a correlator, which is a correlation is a linear operator. So the Gaussian noise statistics stayed the same because it was a linear operation, but now we're squaring it. And so, all bets are off. Things are different. But this is the strategy used in non-coherent detection. So in particular, we'd like to look at phase shift keying and how with phase shift keying we can use non-coherent detection. And you'll see this D appearing, and that is because of differential, and that is going to be the trick we use in order to efficiently do non-coherent reception. So I'll be explaining that now. So why do we have non-coherent? Well, let's contrast this with what was coherent. What was coherent? In coherent, we had the signal which was transmitted. You can think of this as being like the transmitter, put the signal on a carrier. And what did we do at the receiver? At the receiver, we did a correlation. So we took what was transmitted and we again multiplied by cosine of omega 0. And many times I've tried to say that in truth, the oscillator at the receiver is going to be out of phase in general compared to the transmitter one. Now, if I'm using phase tracking, I could use a phase locked loop, add complexity so that I can figure out what this is and I can force it to be 0 so that the two are in synchronous operation. But if I do not want to have the cost of a phase lock loop, a PLL, in a coherent receiver, well then I have to live with the fact that there is some phase which I don't know. So now we can step back and just use a trigonometric relationship so that I know that essentially what I'm doing here is multiplying two cosines. And so I can look at the trigonometric relationship for the multiplication of two cosines. And that is the expression here. And you can see when there's alpha beta, I will get a term which is the sum of the two cosines and one which is the difference of the two cosines. So when I do that for this application, I'll get something which is known as the double frequency term. And the double frequency term is not problematic because it's like quite obvious. So if I'm sending something at 1 gigahertz and then something pops up at 2 gigahertz, well, I just filter it out. It's not going to cause any problem. The problem occurs with this cosine of delta phi because I do not know what value this will be. And because of this, well, here, eliminate with filtering this double frequency term. So what I showed you previously was there's no data yet multiplying by this. This is just what happens when I send two tones. As a tone is sent and then I multiply it with another tone, what happens? But of course, what we're really doing is we're multiplying this by the data. And again, I mentioned if a double frequency term, easy to filter. But now my data here is being multiplied by the cosine of a phase, and I don't know what that phase is. So it's, entirely possible that it could go to 0. Now, if delta phi is itself equal to 0, then everything's cool because cosine of 0 is equal to 1. And so then I get my data right back. But what happens if delta phi is equal to, like pi over 2 or something? In that case, I completely lose my data. And so trying to do coherent detection, try to use a correlator when you don't actually know the phase is like playing Russian roulette because you could just lose everything. So for this, what do we do? So what do I do if this phase is unknown? I can't count on it. So what is the solution for this unknown phase if I don't want to use a phase lock loop? And that is a non-coherent receiver, which brings us into the motivation for the form of the receiver that I showed you at the very beginning. So one way that we could do this is to use a differential approach in particular for the phase. And this is a trick. So instead of using energy as the detection method, what I can do is manipulate the phase even before I transmit it in a way that will facilitate the exploitation of that manipulation at the receiver. So let me try and figure out what I want. So first of all, the motivation. Why are we doing this? It's to reduce cost. Remember, there's three things that count in a communication system. There's BER versus SNR. That's the power efficiency. There's the spectral efficiency. And then, of course, there's cost. And the reason that we would want to avoid phase tracking is because of the cost. We want to keep the cost down. So in this trade-off, I'll avoid that. And so this approach in particular that I'm going to talk about now, the D and the DPSK, applies in certain situations and not all situations. But in this situation, it will work well. And that is when the phase is slowly changing. If I don't know what the phase is, and from one moment to the next, it's moving, and I'm not tracking it. So it's changing. I don't know what it is. Could be going through 0 to 1. You could slow, but it's going slowly. And when I say slowly, slowly compared to what? And well, it's slowly compared to the bit rate or the symbol rate. Then what I can do is I can actually code the information not in the absolute phase, but in the phase difference from one symbol to the next. And so I think I probably should have said instead of bit rate, it would have been more accurate to say symbol rate. So if it's slow compared to the symbol rate, then I can use this trick. And the difference is where we get the letter D. So it's differential phase shift keying. Let me show you how that works. First of all, the form of the receiver. Instead of doing the square law receiver I showed you earlier, we can use one that's even simpler. And in this case, I just use a delay, and I actually use the signal itself to do the correlation. I know that what was transmitted was a cosine omega t, and so if I just delay it, I'm going to have a cosine omega t that I can use as like a self-reference for the detector. So normally I would take the received signal and I would multiply by a separate oscillator in the receiver. Now what I'm proposing in this differential case is not to have a local oscillator. Instead, I'm going to use the cosine in the received signal itself to do the correlation. So we sometimes call this a self-reference of both the frequency and the phase. And you can see this would be a lower cost solution than having your own oscillator. So not only do I eliminate the PLL, I also eliminate the local oscillator. So how does this work? So here is what comes in, right? And I said I had a delay. And so I'm actually multiplying it with the information in the previous symbol interval. So if the information is encoded in the phase, then here's the data at time k, and this is some other data at k minus 1, okay? So when I do the trigonometry, I have the multiplication of two cosines, and I know that this is the sum of cosine of the sum of the arguments and the cosine of the sum of the difference of the arguments. Once again, that's a signal received. This is the self-reference. And when I put them together, I get these two terms. And here, of course, I've got the double frequency term. And in this case, the frequencies cancel out. And so in one case, the double frequency terms can be easily filtered. And so what remains is just this cosine of the difference between the phase in the previous interval and in the current interval. So this, in this phase difference, is where I'm going to code my information. So the actual information is not in the absolute phase at time k or in the absolute phase at time k minus 1. It's in the difference between the two. So logical 0, for instance, could be no phase change. And could be a phase change. And depending on whether I'm doing BPSK or QPSK, that would be how big a phase change I would put. And this is binary, so it would be a pi phase shift or no phase change, but you could apply it to others as well. So remember, I assumed that it is slowly changing compared to the bit rate. So now suppose phi in now is this data rate. This is the difference in the oscillators. So this was the data is in the theta in the theta, and the phi is just the oscillator at the transmitter, which is drifting, okay? So if it's drifting slowly, everything works out. So now I've put that drift in, and you can see why that's the case, because I put the phi in, and you can see that here the phis cancel out. Now if it's not drifting slowly, if it's drifting quickly, then this will remain, and that will mess up my detection. So as long as it's slowly changing, these two things X out, and I really have something which is proportional to the difference. But if I had a fast changing phase, then I would also have in here some drift, and that would mess everything up. For instance, in this former exam question, we have a block diagram which shows the form of the receiver, and in this case it could be, for instance, for getting the I and the Q. So we have an I and a Q. So we're trying to get multiplied by a cosine, multiplied by a sine. So what I do is I use the self-reference. So I come in and I just have a delay, and this is the cosine branch, and then of course I do 90 degrees out of phase, and that gives me the sine branch. And Now I have my coordinates, I could do my arctangent or whatever. I can find the estimate of the phase. And so in this case, I'm saying that the phase is, the drift is about 2 milliseconds. And I ask the question, if I'm using 16 DPSK, can I send information in 1 kilobits per second? And so I have to calculate what is the time of a symbol for 16 DPSK, 1 kilobits per second. What is the time of a symbol? And is this drift changing a lot in the time of that symbol? And then I can answer the question. And so it says justify your response. This is a kind of question I can ask on the exam about DPSK, about make sure you understand the importance of the quantization of how quickly the phase is changing. And so here's just a little trick that makes the receiver very simple. So receiver architecture simple. If I do a clever way of coding the information into the difference in the phase. So again, the important thing is that it is definitely in the phase difference. And if MK is the actual symbol I want to send, then CK would be what I actually put out on my phase modulation. And there's two types of pre-coding that gives you the same thing. That will, these two approaches to pre-coding will both yield a very simple receiver architecture. And it's an exclusive OR operation or the opposite of exclusive OR. They're equivalent. And I'll go through it really quickly just because I want to make sure you get sort of the idea of what's going on here. So these are just, time going on. This is my set of messages, the information I want to transmit, logic 1, logic 0, etc. And I want to differentially encode this. Okay, so let's see how we can use this pre-coding. How does it work? So the pre-coding is based on the message at time k and the previous encoding. And so here at k equal 1, we're just going to assume that the previous one here was a 1. We have to start somehow, so that's the protocol. So now I say 1, exclusive OR 1, take the is 0, and I take the complement, that gives me 1. I go on to the next one. This is used to start the next cycle. Again, 1, exclusive OR 1, complement gives me 1. That's I put in as my code now at time 2. Now at time 3, I take the now I have a 0 as my data, and I have the previous coded bit was 1. And now I have 1 exclusive OR 0 gives me a 1, and the complement gives me 0. So this becomes the new code, pre-coded bit for time 3. And that goes on in that fashion. Excuse me. And then, of course, the last step is I take the coded bit and a transition happens at 1. I have a phase change. And when I have a 0 pre-code, there's no phase change. So that's the difference between this row and this row. So this is the message, this is the coding, and then this just changes the code into a phase change for transmission. So what happens now when I come to my detector? When I do this multiplication by the self-reference. In this case, the detected signal will be based on the difference in phase. So let's look at it now. The estimate of the bit received is the cosine of the difference of the two phases. And here I have the phases that are received. So phase k minus 1, phase k, and of course you have here the difference. So in this case, it's pi and pi. There's no transition, so it's a 1, pi is to 0, it changes, etc. So this makes the receiver very simple, and you can see that because of this phase difference, now what I detect in this difference of phase is directly the message bit that was sent. So just a little trick, use the pre-coding, then when I go into this receiver, the difference pops out right away with the bit that was encoded. So this is the form of receiver for the differential phase shift keying that I've proposed. I said in the beginning that I have an unknown phase that comes in. I use a self-reference instead of the local oscillator. And then, of course, in the second stage, I have the coherent detector, which is really the same as what we saw in the coherent detection results previously. So I never claimed that this was the optimal way to do detection when I use differential PSK. So I propose that I use differential coding. That's what I showed you just now, DPSK. And if I wanted to really have the best possible bit error rate performance, what I would have to do is actually track the phase and use that to demodulate here. And then this is where I would look at the difference in phase, and this would give me better performance. But nobody does it this way. This would be the optimal way, but it's just as expensive as the other. So if I'm going to use differential phase shift keying, I'm not going to use the optimal coherent detector. What I'm going to use is this like super simple, super cheap, easy way to do detection. So now we get into the tricky part. So we have a nice, easy receiver, but I'd love to know, what's the performance of this receiver? And what makes it complicated is the noise calculation. The noise statistics are difficult because think of what's going on here. I have one noise here in the input to the correlation, and I have another version of noise at the input, which is delayed. Of course, they're uncorrelated. However, I take this and I multiply them. So I have noise of t multiplied the noise of t minus capital T. And the problem is that the product of a Gaussian random vector, or a Gaussian random variable, let's say I'm looking at just one sample point, even in that case, it's not Gaussian. So the product of two Gaussians is not Gaussian. The sum of two Gaussians is Gaussian, but not the product. And so what we have in the receiver is a non-Gaussian noise, and that makes things a lot more complicated. So I won't get into the mathematics for you, but it's kind of cool, kind of like it, because you go through the mathematics and actually everything works out really well, and it comes out to be a very, very, very simple form for the probability of error for the non-coherent receiver. But I won't go through that now. I'll just give you the answer. And for BPSK in particular, the form of the bit error rate is 1/2 of the exponential of the negative of EB over N0. And so very, very simple form. If you recall, I think I gave you, when I talked about the Q function, I said that there were a couple of approximations to the Q function, and one of them is with an exponential. And if you compare these two expressions where the Q factor is used for the coherent case, you would see that the bit error rate for non-coherent reception is just a little bit worse than the bit error rate performance of BPSK with coherent detection. It's like 1 dB. So in the end, 1 dB is not a big price to pay in terms of performance in order to have a really simple, inexpensive receiver. So, you could use the approximation here, plug it in here, and look at asymptotically, and you would see it's about 1 dB loss. So, differential phase shift keying, super popular because very, very simple, and the performance not too bad, especially with QPSK.